Give a warm welcome to Sooraj, everyone. Thank you.
So, hi all. My name is Sooraj. I work as a product engineer at Strawberry. So, today's talk is about designing an offline reverse geocoder in Python. So, without any further ado, let's move on to the talk. Uh, Before moving on to talk, let me tell about our company. It's called Strawberry. It's a travel management platform. So, since we are handling travel, the geolocations and geotagging is a bread and butter. uh, but like the conventional players in here like Google Maps or Mapbox, they're providing really good content, but it's very costly for us. And for us it's very rate limiting also, like the bulk amount of data that we are in transaction, it's a very rate limiting for us. So then I came across the reverse geocoding libraries in Python, um, which are really awesome stuff. So this talk would be about my learning about all this stuff. What are the drawbacks I found through my exploration, and how do we actually overcome all this? So yep, let's move on to the next part then. So as you know, like reverse geocoding means like if I'm just giving a pair of latitude and longitude, it actually provides the address of that location. So how it's actually possible? There are multiple ways of doing that. And in the case of offline reverse geocoders, it would be something like this. There would be a list, a finite number of point of interest coordinates for us, which would be having the address. For example, like for example, we have the New York. The coordinates of New York would be already with us in the library itself. And for user just gives a location like this, and it finds the nearest coordinate that is available in our dataset, and it returns the address of that particular location. So that's how reverse geocoding, offline reverse geocoding actually works. So so like you could do this in multiple ways. The naive approach would be take all the list of available point of interest POIs in a list, for example, in a list in Python, and do the brute force of calculating the distance from the user given point to the particular point, and find the shortest distance point and give the address of it. But it may be a right approach for a small amount of coordinates. But if you're actually taking consideration the whole globe, that would be very inefficient, because like that amount of here points are there. So we have a better approach, which is called the KD tree. So how it actually works, these are the x and y coordinates, and we have some, say, random coordinates in it, and we'll be constructing a tree out of it. The specialty of the tree is that it would be spatially related. Like the position of that particular point is spatially related according to the neighbors of it. So let's try to make a tree out of it, and try to query the nearest neighbor uh, inside the Jupyter notebook itself. So this is the sample graph I just made. So these are the point of interest we have. These are the yellow points. Um, so in this case, uh, this is the point that I need to get the address of. Suppose that I have address of all these points. The only thing that I need to know is that which point is closer to it, so that I can tag along with that address. So this is the simplest approach. So I've converted all
Yes.
the marked points into a simple
Hi,
list
Sooraj.
here,
Sorry to
and
interrupt.
let's try to build the tree out of it. So
Hello,
the tree would be looking something like this. So
Sooraj.
before deep going deep into the code, let's see what's the
Sooraj.
approach of it. Uh, so if you
Hello.
look closely into it, you can see that there is something known as an axis. At every level of the tree, there would be an axis present. For example, this is a two-dimensional coordinates, right? 2D
Sooraj.
coordinates, like x and y is there. So every level of the tree would flip that particular axis. For example, the axis 0 means the x coordinate, and the axis 1 means the y coordinate, right? So for every level, we will try to modify the array by this axis. Okay. Then we are going to split the array into middle, from the middle part itself, and give the middle things as the root node, and the left part would be the left node of it, and the right part would be the right node of it. So we have completed the first level of the tree. For the second level, you can see these are the possible values for the levels below. So here we would be taking the axis as 1.
Hey,
Why?
Suraj,
Because we only have this x and y
PowerPoint.
coordinates. So this would be according to the x and this would be according to the y. And here we would be sorting by the y-axis. So that the 4, 7, 13 you could see it's actually sorted according to the y coordinate here. Same here also. Uh, the next thing is again splitting it so that 4, 7 would be on the root node and 9, 4 would be on the leaf nodes of it. So that's how we are. That's the intuition behind creating a tree. So let's see how to do that via code. So these are the points that we actually provide. That this is the coordinates. So initially did that would be 0. So if n is less than 0, which means that we have reached the leaf node, then return none. So like how to make the alternate axis out of it? We could do something like this: depth modulus k. So depth is nothing but the level of tree we have traversed, and k is the plane, coordinate plane, or the dimension we
Suraj,
have, which is 2 here.
hello.
So this is
Hi,
another important
Suraj.
part, that is the sorting.
Suraj,
We are going to sort this the given array according to the axis, maybe the x, maybe y, and finally we would return the center point. I mean the pivot point and the left node and the right node. So it would be the center point of it, which is the flow division of the length by 2, and the next is the left point, which is uh, till n by 2, which is 4, 7, 13 up to 11, 10. And the right point would be from n by 2 plus 1. Y plus 1, because 11, 10 is excluded. It's already in the root node, right? So it would be taking from 15, 3 to 19, 11. And of course, it's going to recursively code until the root node is reached. So every time the depth would also increase. So let's see how it actually looks. So yeah, we have got something like this. This is the array, sorry, the tree that we have built, that is 11, 10, 4, 7, 16, 10, and so on and so forth. So if you look into the coordinate plane, this splitting, what actually does is that we have initially, this was actually the coordinate plane, right? We have split that initially by the center of it, which is 11, 10. Then it was an split by the x-axis. Then we split by the y-axis. Then we again split that, but this area by this and this area by this point. So it's kind of a splitting into subregions. So we got the tree. So now let's try to find the nearest point. Uh, Before finding the nearest point, we need to have some kind of utility functions for it. So first thing is to find the squared distance. As we know, like we are handling with coordinates or general coordinates, then you need to find the distance between them. So how to find that? X1 by x2 minus x1 into y2 minus y1. That is this. It would be always positive. Like we are actually taking the square, so it would be always positive. So that's how we actually going to find the square distance. The next is the closer distance. As we say that we are going to compare it with the all nodes, right? We need to compare it all nodes to find the best closest distance, right? So we need to have a utility function for that also. So the pivot point is the point we are interested, and P1 and P2 are the comparing points. So we'll find which is closer to the pivot point and return the distance. So one thing to note is that even one of it is none, we will return the other, so that unbalanced trees could return the data also. So yes, um, so now let's see the intuition behind it before diving into the code, how to find the closest neighbor. So again, we are just going to give the breaking condition. If the root is done, return none to um, for the recursion to come back after the execution. So again, we will find the depth. The intuition behind it is that suppose the point that we need to find is 14.9. Okay, suppose the point we need to find is 14.9. I will compare it with from the root node itself. So it is 14.9, right? And if you check closely, you could see that the left side of the root node has the value of x is less. That is the axis value 0 is less in the left side. On the right side, the axis value is more. So like it's kind of an there is a hierarchy in the coordinate system itself, right? So in the case we are actually going down, the y-axis in the node below has a greater value than the left y-axis, which is 4, right? And which is also less than the right value, which is 13. So these guys are actually hierarchically organized so that it's very easy to compare between these values. Okay, suppose if I have a value like 14.9, right? I will instantly compare with the root node. So I need to have a value 14. So let's compare with the axis of 0, that is 11 itself. So in the case of it, it's greater value, right? So the next root should be the right value. I mean, the right part of the tree, not the left part, because if the left is less than the root itself. So since 14 is greater, I need to check for the right part. So I came here. The next thing is 14.9, right? I need to check the y value. So the 10 is greater than what the 9 itself. So I need to find value less than this particular node. So I need to move to the left pole. So that so this is the intuition behind it, like finding the uh, minimum value difference to every access point at every level. It's the intuition behind it. That's what we are going to do. So let me just comment down this code and see what happens. Uh, so we are actually going to compare that particular point to every root node and see if it is less, that it would be the next point. Otherwise, it will be the right part. Okay. So if you're actually going to do this, there's a caveat in it, which will be explained later. But so the best is nothing but the closer distance. If you see the closer distance, it takes 3 points and gives the closer point, which is either P1 or P2. So this actually goes deep into the tree and gives the most optimal solution. So if you try to run this, I'm going to get the answer as 1610. But if you look into the graph, Windows 1610 is closer, but it's not the best answer. The reason is that we have like our recursion tree was something like this. We go from this to this node to this node, but actually we didn't check this part of the tree. If we have done that, like we would got the the closest point right there itself. So so there is a general equation for it. That is the distance squared between the best point and the current point. This is the point of interest. This is the point we are trying to reverse geocode. Is greater than the access point between that current level. We could actually check the other node also, right? So we'll just go straight and check the other node. So for that we'll be checking with the point, and KD tree closest point will go down to the tree, to the lowest level of the opposite branch, and find the best match on it, and it will be compared with the current best. So that if you are doing like this, you will get the uh, most closest point there. So that's the basic idea of a KD tree. That's how we are actually going to find the closest neighbor. Um, so yes. So we have gone through the naive approach using the Python KD tree. So but this can't be used. I mean, the version I was shown can't be used in production because it's for larger data sets. It would be comparatively slow. But we have another alternative. Thanks to scikit-learn, they have a module for cKDTree, which is essentially the C version of it. So you could use it similar to what we have done. We just build a tree. Note that we are actually using the NumPy here. Okay, and you'll just give the query points. We have only given a single point, but you could actually give multiple points here on KD tree from the SciPy to query, and the k is nothing but the nearest neighbors, number of nearest neighbors that need to be queried. You could give it to k1 to n number, like till the end of the array. Could give any number to it. So you could use it. It's very fast. But the interesting thing regarding that is that it actually returns the indices. So this is very important regarding in the reverse geocoding purpose, because uh, the inside the KD tree, like the mathematics and all this stuff will be done by the coordinates, but as a human, we need to get the the address of it ultimately, right? So you could actually tag this particular coordinates via metadata, and you could use that particular index to get that metadata. For example, you're storing all the coordinates into a CSV, uh, and you could actually just give it straight to the tree to query, and it will return the indices, and you could reverse look up the CSV to get the address of that particular location. So in the point of reverse geocoding, it's very useful. You also can get the distance of it. Another important thing regarding the KD tree is about the leaf size, which is the minimum number of the coordinates or the points in the leaf node to do brute force approach, which means that if the elements in the leaf node is less than the leaf size, could switch back to the you know brute force approach, which is calculating each and every points inside in the lower level of uh, you know the tree. For example, let me show you. Suppose this is the tree, and if the leaf size is, say, I'm giving the leaf size as, say, 16. The default value is 16. So any value below that, rather than splitting down to anymore, it will just brute force distance between all the neighbors and give the result. So that's a really good thing. Like it avoids unnecessary recursive paths. So yes, the advantage of using this kind of this modules is that it is implemented in POC. It's very faster. Okay, like it's uses the pointer arithmetic, which means that it's actually changing directly via the pointer address itself. So it's very fast. NumPy arrays are used. Another important thing is that it releases GIL during queries, so that parallelism, a sense of parallelism actually uh, go through it. So we actually got the we have actually learned how to get the nearest coordinate from a given coordinate. So how to make a reverse geocode out of it. So as I said, you could actually tag it with some metadata and reverse lookup into it, so that this getting the nearest address would be very easy. So one optimization that could be done is that for large amount of data, you could actually do it into a multi-process. Rather than depending on the single process, you could do a multi-process, so that each core will be having a slice of data to reverse you. So yep, that's it. So if you are following me this far, you may have some doubts whether how accurate is this. So for example, this is the this is the location I want to reverse your code, and suppose these are 2 points that I have as a point of interest. Unfortunately, this is the closest point to mine, but it's actually in New Hampshire. But my point is actually is on the other side of the boundary, which is in Vermont. So unfortunately, it will give the answer as Lisbon, New Hampshire, because the closest point is this. The KDT does not know which boundary is it, right? So that's a major disadvantage of using like this. So like as I said, we were actually using this for our trial products. The major disadvantage was this ambiguity. Um, so I came up to a conclusion that whether we could actually restrict this kind of ambiguity by by their boundaries itself, so that a boundary check, suppose if I'm just giving a boundary check for this point, it will this will be still a neighbor for it, but since the boundary is this side, it will go to Vermont rather than pointing to New Hampshire, right? So I try to find the best geo boundaries data sources, and hopefully I came around geo boundaries which are handled by William and Mary Geolabs. So the important thing about it is that uh, they are just giving the best available open source data for free, and they're actually manually verified and taken from authoritative sources. So, and also there are correctly divided divisions for it. For example, there is they are from actually administrative division 0 to administrative division 5. So the zeroth division is the country itself, the boundary of country itself, and administrative 5 is the lowest level you can find. Um, so we got a really good source of boundary to validate whether this reverse geocoding point belongs to that point. And but since it's an offline reverse geocoding library, I can't store all the coordinates of the planet Earth into some disk, right? So it will blow up my disk because that much amount of data is there. So thankfully, they also provide an optional simplified boundary regions, which means that they also provide the simplified boundary. Uh, there are several options of their datasets. The first is the highly scientific, highly accurate boundaries of it. Then other is the simplified boundary. So I opt for the simplified boundary because like that was only the need. I need to restrict it rather than using for another scientific purpose or something. I need to. The restriction was the main aim of it. So I opted for the simplified boundary. You could check out the journals here about the blogs and all things that are written about geoboundaries. So, so how simplifying JSON or GeoJSON? So the boundaries are actually given in the format of GeoJSON. So, like as I said, I can't take all the boundary data and store into my local machine because like it's very heavy and the data is very much high, and I can't shrink it in a Python package size. So I need to simplify the JSON. Uh, since GeoBoundaries itself just provides the simplified JSON, I guess it's not documented anywhere, but I guess it would be Douglas-Baker algorithm to simplify the GeoBoundaries without losing its shape. So these are the full resolution, and these are the simplified boundary. Even from the distance, you can't spot any changes in the size or dimension of the map what you're seeing, but it's a simplified size. I mean, the size difference was around 8 times, I guess, when I downloaded the dataset. Okay. So I opted for the simplified version. Another thing is, even I tried the simplified version, it was still huge for using inside a library, because like this library should be packaged and shipped to the cloud so that everybody could install. So I don't want my library to be in GB size, right? If you're considering the whole world and if you're doing like that, it would be around 1.5 1.6 GB. So I have to find another way to shrink down the size. Then I came across the well-known binary format. So as you know that GeoJSON has a format. Like there is some type would be there, then would be the coordinates, then would be feature collection. I will show you GeoJSON later in this talk. So anyway, we'll convert that into a simple binary value, and we'll use that for the computation purpose. The highlight was that it was very much, the size of it was around 8 times smaller compared to the equivalent GeoJSON. So thus I also got size reduction via using that also. So how it's actually done, how it's stored, there were multiple ways of doing that. I initially tried Parquet, storing it as Parquet files and using it on the go. But like the issue with the Parquet files was like I need to store it as a file. Like the every time the user sees a library or even seeing the source code, like there will be tons of Parquet files that need to be shown. Like there are about 1 lakh, I mean 150K, you know, boundaries that we are interested. So I need to at least make 150,000 uh, Parquet files for it. So it seems to be a very ugly way of doing that. So uh, I opted for using an SQLite, simple SQLite DB, just to store the well-known binary files of it. So there should be some unique way to find the boundary, right? So thankfully, geo boundaries also provide the shape ID. I'll show you what all these things are actually. Uh, so, for example, this is um, this is a GeoJSON. You could actually see this is the format of GeoJSON. Like the feature collection is there. The format of it. and features. I mean, like this is the standard format of it. And okay, this is where we are actually going to convert into a well-known binary part. So this is actually the file that we got from the GeoBoundaries itself. So it's about the states of United States itself. This is the shape ID, which is globally unique. You could get the country where it belongs, so and so. So there are multiple ways of accessing a GeoJSON file, and then the simplest version of it is to use a GeoPandas itself. So let's see. We are using GeoPandas, and we're simply reading the GeoJSON, and we are just converting that by using a lambda function to WKB format, right? So yes, it's a binary format. You could see X and all these things around there. We have about 55 number in it. So this is how we actually going to convert into well-known binary format and store it in the DB. So so we got the reverse geo. I mean, finding the nearest neighbor part to be done. Then for finding the validation part, we have also got the source, that is the geo boundaries data also here. So the only thing remaining is to check both part together so that a validation would be at the end part of reverse geocoding. So as I said, I would be using the you know saving the WKB files inside the SQLite itself, so that it's actually very easy to access. I could run queries on it, and yeah. So and very and we could actually use the validation part, which is like if you're actually using the converting the WKB into polygon, you could actually use contain in Shapely, right? Which could be used to validate among the nearest neighbor to find which point is actually which polygon is actually inside the given coordinate, and give the exact address of it. So for that, let me walk you through the comparison. So I just made a library which is called RetroGeo. I have not yet released it to the PyPy. This version of it has not yet been given to PyPy. So I have to install it by wheel file itself. And for the sake of comparison, I'm going to use the RGeocoder, which is actually a Rust-based geocoder, amazing library. And let's try to compare it with a location from a Google map. Okay, suppose this is the location. We'll actually see it. Um, the one part is actually Vermont, and the other part is New York. Reach out and see. Yeah, one part is actually Vermont, and the other part is actually from New York. And suppose if you're using the RGO coda, since they are actually only considering the nearest neighbor, it will just give Washington, but actually it is in Vermont, the other state, right? Since it is close to the boundary, it's giving me the wrong details because the city is closer to the New York itself. But if you're actually using by the final validation using the SQL, you could actually see it as the Vermont itself, it is Bennington. So yep, that's how it actually works. That's how it actually makes it the correct boundary. So and the final part of the presentation, which is benchmarking. So I've opted for two type of calculating the address, that is a single process or using the multi-process. So if you could actually see that this is the number of locations I've given to reverse geocode, and this is the time taken for it. So for the initial number, like a very small number, thousands or 10,000s,